Okay, so part C, we're going to have the integral, indefinite integral of 1 divided by x squared minus 4x, the whole thing to the 3/2 dx. And x, we're going to say x is greater than 4. Can anybody see why just by looking at the integral? Why x better be at least not equal to 4?
Because you have a square root, so you don't want it to be inside the negative.
Well, yeah, that goes even further. Yeah, so for the x to not be equal to for x to be equal to 4, we'd have what kind of problem? Division by 0, right, in the integrand. Because you plug in 4, you get 4 squared minus 4 times 4, 16 minus 16, 0. Can't divide by 0. But also, you have a 3/2 power there, which is like a square root to the 3rd power. And you, like you pointed out, you can't even have a negative there, can you? Underneath the radical, that is. So that's why x has to be bigger than 4 for this stuff to make sense. Okay? So we've got a little restriction there. All right. Does this look like any of those forms from the beginning? X squared minus 4x inside. So look inside the grouping symbol. This is a kind of root, right? The 3/2 power is a kind of root. So it makes sense we might try a substitution, but does it look like any of these? Does it look like the square root of a squared minus x squared? Does it look like the square root of something squared minus something squared? Does it look like the square root of something squared plus something squared? Or the square root of something squared, something involving a variable squared minus something squared? Well, it doesn't quite look like any of those because, well, the x squared's fine, right? But the minus 4x, it's not a constant squared, is it? Which is what we'd like it to be, but it's not. So guess what we get to do here? To make it look like one of those forms, we get to do something that you loved from algebra. I say that very sarcastically for most people. We get to complete the square. I saw the look on your face. Okay, you weren't too happy about that. I know, but I'll make it as painless as possible. So what does that mean to complete the square, you guys? What does that mean to complete the square? We want to add something. I'll put a box. We want to add something so that that trinomial factors to be a perfect square. Right? That's what it means to complete the square. Well, you might know right off the top of your head what it is. What does it have to be? It's 4. Yeah. But let's talk about the process for getting the 4 there. So the process is as follows. Okay, first of all, you got to have a 1 in front of the x squared. If there's not a 1 in front of the x squared, then you're going to have to factor out whatever the leading coefficient is from the first 2 terms to get a 1 there. And we'll cross that bridge when we come to it. We have a 1 there. We're good to go there. So now, once you have a 1 in front of the x squared, you go about the process of finding that number you add in that completes the square for the trinomial. And remember, the process is to take half the coefficient of the x. Remember that? And then square that, and that's what you add in. So let's try that. What's half the coefficient of minus 4? So that's minus 2. And then you square a minus 2, you get plus 4. Now, the problem is, by just adding that 4 on, we've changed the value of this thing, haven't we? So what do we have to do to compensate? Subtract 4 right back off again. That old trick of adding and subtracting the same thing, which the net effect is adding 0. Remember that trick? Okay. So then this, you factor just the first 3 terms. And it factors to be x minus 2 quantity squared minus 4. Now, do you see the form that this is in? Do you see why this form is correct? Because we've got something involving the variable squared minus some constant squared, 2 squared. 4 is 2 squared, right? So of the 3 forms, which does this look the most like? I know it's hard to see. I shrunk it down, so let me zoom in a little bit. Of the 3 forms, which does this look the most like? The third form, we've got It's not exactly like it, but we've got the variable being squared underneath the radical. We've got the variable being squared minus the constant being squared. So it looks the most like that. And when it's in this form, the substitution is x equals a secant theta. So we just have to figure out what we should be calling the left-hand side of this substitution, and then what a is. And then we're in business. Okay. So generically speaking, the substitution is x equals a secant theta. But we have to adjust. We have to adjust this. Okay, so what's acting like the x here? What's acting like this x? X minus 2. So x minus 2 is going to be, that's what we're going to replace this left-hand side of the substitution with. And then what's acting like a? Yeah, just 2. So x minus 2 equals 2 secant theta. Okay? Now, why is this helpful? Well, hopefully it's going to make that. Do you see the fractional exponent? It's the denominator that tells you you're dealing with a square root. So we're hoping that by making this substitution, we make that denominator in the exponent go away. Okay? That's what we're hoping. So let's figure out what dx is, and then we'll make the substitution. So what's dx going to be? You could add the 2 to both sides to get x by itself, but when you take the derivative, the 2 gets obliterated anyway because it's a constant. So dx is equal to what? Well, 2, the constant stays attached to the function. What's the derivative of the secant? Secant theta tan theta. And then don't forget the d theta. Okay. So here we go. We're going to put this guy in. Oh, you know what I should probably do, or what I probably should have done, just to make it very clear in the notes. I probably should have rewritten the original integral with the completed square form of that denominator. So let me rewrite this guy as the square root of 1 over, it's this guy. We completed the square on x squared minus 4x, got this guy, x minus 2 quantity squared minus 4, and we'll put that whole thing in brackets and then bring it to the 3/2 power. So all I did was rewrite the integral. Let's go ahead and make the substitution. So this guy, x minus 2 equals 2 secant theta. That 2 secant theta goes right in there for x minus 2. And then, of course, for dx, 2 secant theta tangent theta goes in right there. And we're hoping, we're keeping our fingers crossed that this cleans up nicely once the smoke settles. So we get, okay, down here we get 2 secant theta quantity squared. I'll go ahead and show all the dirty details, and then I'll clean it up. So that's in place of x minus 2, and then we still have the minus 4. We need the 3/2 power, and then the dx is 2 secant theta tangent theta d theta. Any questions so far? Now it looks pretty ugly, but again, we're hoping to use we're hoping to clean it up algebraically and then use a trig substitution, or a trig identity rather, and then hopefully it cleans up nicely. Okay, so this guy right here inside the brackets is really what? 2 secant theta, the whole thing squared, is really 4 secant squared theta minus 4. So what can I factor inside those blue brackets there? What can I factor out? The 4. And I get 1 over, brackets 4 times what? Secant squared theta minus 1. And then we still have the 3/2 power here. Everything else, just recopy it. Okay. And then what is the secant squared theta minus 1? By just a trig identity, what does that equal to? Tangent squared theta. So it is working out. So far, so good. So we have to the 3/2 power. Okay. Let me put the 2 secant theta, tangent theta on top. And then we have 4. Well, let's go ahead and take the root. So if we go ahead and take the square root of both the 4 and the tangent squared theta, what does that leave us with? Square root of 4 is 2. Square root of tangent squared is tangent. And then we still have an exponent on the outside, right? What is it? It's this exponent right here didn't go anywhere. I applied the denominator of the exponent corresponds to the root. I applied the square root, but I didn't do anything there. So you could either, well, I think I will actually do it in this step. And then we still have the d theta. I'll do some erasing and do it in this step. So does everybody agree with that so far? Is that okay? But if you wanted to skip that step, how could you just rewrite it without these brackets here? Well, because it's a product inside those brackets, that exponent applies to both factors in that product. And so that's how I'm going to write it. I'll simplify it in the next step. Any questions on that? Okay. So this becomes 2 over 8, right? 2 cubed is 8. So what does that reduce to? 2 over 8, 1 over 4. I'm going to pull that out front. And then 1 factor of the tangent here will cancel with 1 there. And what will we end up with? Secant theta over tangent squared theta, I guess. Does everybody agree with that? Okay. Now looking at this, I don't know if it's immediately obvious what method to use to integrate this. And you could play with it for a while. You could try one of the tricks I gave you yesterday. But I think it's worthwhile just to check to see if it turns out nicely when you convert to sines and cosines. Remember that trick when you were proving trig identities back in pre-calculus? If you don't know what to do and the identity involves like secant or cotangent or tangent, try converting to sines and cosines. Well, we're not proving an identity here, but that trick or guideline still might apply. So, okay, a secant theta, what is that? That's 1 over cosine. And tangent squared theta on the bottom is like having cotangent squared theta on top, right? So what would that be? Cosine squared over sine squared. So do you guys see what I did? I rewrote this guy, secant theta, as this guy. And now we just get as our integrand cosine theta over sine squared theta. I think that's worth doing. I think we know how to integrate that. So it didn't take very long to check, and we got something that I think we can use a U substitution on. So this goes back to techniques from, I guess, the second section in the chapter. What could I let U be so that I get a nice du? Just sine, yeah. If you let U equal sine, then then du is cosine theta d theta, and you've got a nice factor of cosine theta ready to go. So a nice way to see that is if you rewrite it as 1 over, or even better, sine to the negative 2 power, and then cosine theta d theta, and then let u equal sine theta, and then it's like the du is gift wrap for you. Du is equal to cosine theta d theta. But without actually making the substitution, then I think I can do this. I think I know how to integrate. Essentially, this is sine to the negative 2 is u to the negative 2 power. I think I know how to integrate that. What do you guys think that is? So 1/4 times, okay, add 1, divide by the new exponent. What do you get? Sine to the negative 1, divide by negative, you just get negative. Sine negative theta, or negative sine to the negative 1 theta. And then, well, that's it, isn't it? Well, plus c, I guess. And then, of course, we have to convert back. Does that make sense to you? Is that okay? All right. So you could write it like this: negative 1/4 times 1 over sine theta plus c, if you like. Well, we got to go back and make our helper triangle, don't we? So if we go back and we make our helper triangle, you have to kind of go and look at the original substitution. The original substitution looked like this: x minus 2 is equal to 2 secant theta. But I think it'll be helpful to solve it for the secant of theta to get the correct ratio. So what does the secant of theta look like? There you go. Okay, so which on our helper triangle here, which side are we going to label x minus 2? And then which side will we label 2? There we go. Any guesses as to what the opposite side is going to be if you apply the Pythagorean theorem? Right. I believe that's right. And it will also be the square root of x squared minus 4x. And you can check that using the Pythagorean theorem. It's easier just to take the two legs. Okay, you get 2 squared plus this guy squared, and you'll get this guy squared. And it's going to be true. You can check it on your own, I guess. Okay, so looking at the triangle, what do we get for 1 over the sine of theta? I guess that's the same thing as the cosecant, right, if you want to think of it that way. Anyway, what do you get? It's got to be the hypotenuse on top, right? Because normally sine is over the hypotenuse. It's opposite over hypotenuse. So it's got to be x minus 2 on top. And then what goes on the bottom? Yeah? You guys buy that? And that works. You could put that 4 in the denominator if you want, but that works as it is.